we're measuring not the disappearance or removal of a particular wavelength, but the appearance or generation of photons in a particular wavelength that we measure. So in both cases, we like to think that the lines are perfectly infinitely narrow, but they're not. Right? There is somewhat of broadening of these lines, and that broadening of those lines, and I'll talk about the kinds of things that can affect the broadening of these atomic spectral lines, sometimes can become an issue if the spectra, the atomic spectra, has atomic lines that are too close to each other in their energy level, in their wavelength. Okay? Because they can start overlapping. Right? And then we start losing the relationship between a single event of absorbing an incident photon and the excitation of a single electron and a single atom to a higher energy. So that's what this is saying here. So the reality is that when we look at atomic absorption lines, that they're made up of sort of a symmetry of distribution around a mean wavelength, which is what this is supposed to reflect. So the atomic spectral line, for example, for copper that you're using at 324.8 nanometers, would be the mean spectral line of copper, but it's not just a straight line. There has some deviation of the wavelength around that mean spectral line that reflects some broadening of that due to a number of factors. Okay? And the things that can contribute to that spectral line broadening, which would then potentially contribute to overlapping of adjacent spectral lines, which would then create a potential problem that would actually be manifest as an interference in your measurements, is a number of processes that are occurring within the flame and within the environment where the photons are interacting with your analyte atom. And some of those, like in the category of natural broadening, is because you have the excitation of electrons to a higher energy state due to the absorption of the incident photon. Okay? And there's some slight variation due to those atoms interacting with each other and smashing into each other in that flame thermal environment. Slight variations in how long those electrons remain in the transition in the higher energy state before they fall back down. In all cases, when you have your atom that absorbs the photon and gets excited, then that electron is going to fall back down to the ground state, and then of course it's a release the emission photon that we don't care about or we don't measure. It's a different wavelength, right? But there's a lifespan that atom remains in the excited state. And that lifespan that atom remains in the excited state, it determines to what extent it can then fall down to the ground state and then absorb another incident photon, right, before it actually leaves that environment of the flame. So some of these processes are like natural broadening, which is uncertainties in how long those atoms are in transition to excited states. When you have these atoms in different states that are colliding with each other because there's high thermal environment, there's a lot of energy, and they're moving around really quickly and colliding with each other, changes that as well. Power broadening in terms of the lifespan, because you have emissions. Some of these photons, when they fall back down, is they would then produce an emission photon of a different wavelength, and that emission photon of a different wavelength can interact with adjacent atoms, right? If they happen to match exactly the transitional energy there. And the last, the Doppler broadening, is the reality is that when you have that flame environment, and you have photons coming in from one side and then passing through or not from the other side, and the temperature, is that you have, in that thermal energy, you have those absorbing atoms moving in many different directions, right? Up and down with the flame, as well as laterally, because of the thermal energy that's in that flame. And that movement within there, relative to the photons that are coming in, can create some actual Doppler broadening, which is essentially reflects that you're getting a change in the apparent absorption of that photon based on the velocity of that atom moving relative to the photon. What does that mean to you, all these things? It means that you have, in reality, not these distinct, exactly sharp atomic spectral lines that you are dependent upon to provide a very quantum of energy that you can absorb with your analyte, but it means instead that you have a slight broadening or distribution of these spectral lines around a mean spectral line that we rely on. And depending on how close these spectral lines are for a given analyte, determines how much potential overlap there are between adjacent spectral lines. And the more overlap there is between adjacent spectral lines because of this broadening, peak broadening phenomenon, then the more of a problem it potentially is for us to use those spectral lines in atomic absorption. And that's the problem. Does that make sense enough? Yes? All right. So, okay, so blah, blah, blah. Yeah, so we just talked about this. This is, in this case it's nickel. That's a very simple nickel spectral. The spectral lines for nickel, and I'm not going to play that anymore. All right, so we talked already about the other component in absorption spectroscopy. And so we know that we are generating electromagnetic radiation to interrogate our sample. In UV vis, we use the deuterium arc lamp to generate broadband light. Right? In atomic absorption, we're using a very specific source of light that generates wavelengths of light, spectra of light that are match exactly our analyte, because the light source is made from our analyte, copper or lead or whatever. In all cases, we still have to, when we generate a complex atomic spectrum like this, we still have to select one particular spectral line in which to interrogate our sample. Right? And that's very important. Just like in Beer's law, even though it doesn't apply here, just like in Beer's law, the assumption is that the light that we're interrogating our sample in is monochromatic, right? Of course, that's not true. We violated that, but we constrained it, violated it not too severely. It's the same assumption here that for atomic absorption, that we are assuming that the light that we're interrogating our sample with, that we're measuring the absorption of, is monochromatic. And so we have to, of course, generate monochromatic light. But where we generate that light is a little bit different here than it was in the UV vis. We'll talk about it in a second. The way it's done for atomic absorption is the same concept than the way it's done in the better UV vis spectrometers. And that is they use diffraction gratings, which again you remember are highly polished, typically metal, highly polished metal surfaces, not this big, but maybe about this big, a couple inches square or so. That have these laser etched grooves at very specific angles and creates this gradient. And those angles that are etched into that highly polished surface are such that they reflect light at different wavelengths, at different angles depending on the wavelength. Okay? So in this cartoon coming in, you see that the incident light is coming in at the parallel to the same wavelength, and it's going out. Can't quite tell here, but it's supposed to show that it's going out at slightly different angles. And so it reflects the light at slightly different angles depending on the wavelength. And many of you know that because that was on one of the quizzes. You got that right. And so in an atomic absorption spectrometer, where you take an example like this, and when the light is coming in and it gets moved around by the optics, is you're able then to reflect light at different wavelengths so that it then goes through the exit slit can interrogate your sample, as an example, right? And the wavelengths you don't want are reflected and don't pass through that slit. Okay? Because you can rotate this grading to determine which wavelength actually lines up and goes through that. And so in your instrument, when you dial in 324.8 nanometers, this is what the instrument's doing. It's rotating that grading in order to, that it knows what to do, in order to push the 324.8 nanometer wavelength through that slit. Okay. And this slit's relatively narrow, and the grading is quite sophisticated on these instruments compared to, in terms of how finely graded they are, compared to UV vis, because they have to separate wavelengths that are much more discrete and defined. But they do that. They do a pretty good job of that. All right, so this shows us a little bit better. In this example, these are lights of wavelengths, and you can see these are coming in exactly, supposed to be the same trajectory, but it's coming out and being reflected at different trajectories because they have different wavelengths. That's what I was supposed to show. Okay, This shows it even better. Like this. So here's the light source going through an instrument slit, okay? And it's all white light, you know, and it contains 3 spectral lines for copper, let's say, and it is reflected through this concave mirror to the diffraction gradient that can rotate, and then the diffraction gradient then is now separating that light, that polychromatic light, into its multiple components where it's reflecting the different wavelengths at different angles, and now they come out at separated wavelengths, and it's moved the diffraction angle on the grating so that you're selecting for the green light and not the red and blue light. So it's pretty straightforward that way. They're pretty ingenious way to achieve that control. So now for flames, we've seen this before. So we have our light source. Then we have our, essentially our volatilization source, right? It's going to take our sample from the liquid and turn it into free atoms, which is the flame. And then we have our monochromator, and the main component of the monochromator is what? What's the main component? What's the main component of the monochromator?
Diffraction.
The diffraction gradient, right? We just talked about it. The diffraction gradient is inside that, right? And then we have the detector, okay? So in this case, for flame, and it's this way for a lot of atomic absorption instruments, why is it the monochromator here comes after the flame? Your sample is there in the flame. In UV spectroscopy, the monochromator came before the cell, for your sample cell, right? But here, the monochromator diffraction gradient is coming after the flame. Why is that?
I mean, we use the hollow cathode lamp with the copper light. I mean, we're going to have a bunch of different spectral lines, right? But we're only interested in the one that has the intensity that we want, and like the, what was the reviewed non-interference that we want? So is that why? So we're really only interested in 3.8, 24.8.
Okay. But you'll achieve that no matter where it is, whether it's before or after the flame, right? You'll achieve that.
The flame is going to generate its own light wavelengths.
Yeah, so the flame is, it's a light. The flame's generating broadband electromagnetic radiation. If we had the monochromator before the flame, we'd be selecting for that very specific spectral line of copper. And then we'd hit the flame, and there'd be all this light coming out of the flame, and the detector would be like, whoa, I just see a lot of photons, right? And so we've got to be selective after all that, right? And so there's a lot of absorbance going on of copper and so forth in the flame, by copper in the flame, across these different wavelengths, right? But the only wavelength that we're measuring, that we care about in terms of absorbance, is the one we've selected, 324.8. Copper atoms in there are absorbing light from many other sources of that copper spectra, but the only one that we're monitoring for absorbance is the one at 324.8. And I'm getting rid of all the light from my flame by doing that. And in this case, I'm able to look at what's coming in and out. Well, let me back up. So how about, if we have it there, how is it we're able to actually measure light at the flame light that may be at the same wavelength as the copper that we're generating? If the flame is generating electromagnetic radiation, it's broadband. So we'd have sort of an absorption spectra. This is for copper. Say this is for 324.8, the one we want. And here's what the flame looks like, right? It's broadband. How are we going to distinguish the absorbance from this copper line due to absorbance of that, of the flame? Okay. And well, the way it does it is it has a new thing there, not new to you, called this little rotating chopper. It's like literally a fan kind of thing. And what that fan does is it is essentially blocking the light coming from the hollow cathode lamp. It's rotating at some known rate. And it comes before the burner, and as it rotates, the detector is measuring photons. It's measuring photons when the lamp is just being blocked. So this is only the flame. and then it's measuring all of them, and it gets this square wave signal that can distinguish the difference between absorbance through the flame, photons generated, versus a hollow cathode line, which is specific to copper. And the instrument electronics handle that and generate a absorbance signal for us that reads out for you that actually already corrects for that. So these guys have thought of everything. Okay. The last, I'm going to talk quickly about this and we'll back up next time. So at the very end of the instrument, you have to detect those photons. And just like in the UV viz, we talked a little bit about this, but not in any detail. Spectrometers that are measuring electromagnetic radiation most commonly use photodiode or phototube detectors. And they're relatively simple. This is sort of a electronic diagram of what they look like. That they have in the detector, which is this round thing, the cartoon version of it, is that they have a photocathode emitting surface. And it's coated with material that undergoes the photoelectric effect. What that means is that the material on this surface, when it is struck by an incident photon coming in from our hollow cathode lamp that didn't get absorbed, right? When the photons strike that surface, it causes the release of electrons from that surface because it's the electron-emitting material is coated on that surface. And the surface is functioning as a cathode, and in the middle in this cartoon is the anode, and those electrons that are emitted then are attracted towards that anode. And that is then measured as a current. Right? So the more photons that come in, the more electrons that get bumped out, and get measured as a current, and you get a higher current. So it's an analog version of converting photon intensity to current. And that's what a readout is. Essentially, you're getting a relative current in terms of absorption in a relative absorbance units. That's the current on that detector. So you're taking photons, freeing up electrons that are kicked off that photo sensor coating surface, and generating electrical current as a result of that. Photomultiplier tubes, which is actually what yours has, take that exact same concept, but then are far more sensitive because instead of having just one cathodic surface, a photocathode, they have many dinode cathodic surfaces. And so in this example here, where the anode is here, and this might be the photoemissive cathode surface here, the incident photons would come in, and they'd strike, and they'd absorb a photon, and it would kick out an electron. So you've now converted a photon into an electron signal. At one electron in this cartoon, at one, or usually probably like those 10,000 electrons that would get emitted from the one photon event, would then get attracted to this dinode surface and strike it, and those electrons would cause the kicking off of 3 times as many electrons. And those would get accelerated to this dinode and do the same thing, and you then are magnifying the number of electrons that are being released from that initial event from 10,000 to maybe 1 million. And so in terms of the sensitivity, they're far more sensitive because you're generating much greater current with electron flux from that one event than you would be if it were just a straight photocathode. And that's what yours is. All right. Let's stop now. Okay, let's stop now. So you guys have all gone over method of additions, right? In class? And you think you were clear because I made this clear, I think, to both sections that you were going to have to measure copper and lead, right? You're going to have to do replicas prepared. Now, on the AA instrument, it's quite easy to hit read 10 times. It takes like a half a second, now you said the read cycle, but it can take just a half a second to do a reading. And so hitting read multiple times does not count as replicate measurements on your sample. Right? All that counts is it tells you something about the analytical noise, which is important, but it doesn't count as replicate analyses of a sample. And replicate analyses of a sample, we've all talked, is taking an unknown like this, where you say, I don't know where this came from, but this is my world. And I want to characterize what's, as well as I can, estimate what, as best I can, what the concentration of the analyte is in this unknown big bottle. And the way I do that is not by taking one flask and measuring it 100 times, so taking 5 seconds. The way I do it is replicating the whole process and how I prepare it, where I may take up 3 different containers and prepare them in triplicate, right? We've talked a lot about that. This range, this level of replication is what is necessary to best characterize the reproducibility of your measurements and the best estimate of what is in this unknown jug, right, which is your goal. If you want to measure each of these 5 times or 10 times, that's totally fine, right? But at the end of the day, it's this replication that determines the variance of this number. It's not how many times you measure each of these. Is everybody clear on that? Right. So one thing you're going to be doing is doing replicates on this, and the replication is in replicate processing of that original sample. Right. That's very important. The next thing you're going to be, so that's going to tell you about your reproducibility or your precision. We talk a lot about that. Right. And now for the accuracy, you are being tasked with performing a method of additions. Many of you for Lab 1 attempted and performed a spike recovery experiment, which is the sort of the baby brother version of a method of additions, right? It actually accomplishes something a little bit different than what this does. It's still valuable, but it's not as rigorous as this is, okay? And so you're all being tasked with now performing a method of additions on both unknowns for both analytes. Right. And so now I want to make sure, how do you go about performing or setting up a method of addition experiment? First of all, what's the concept, what's the purpose of a method of addition experiment?
Make our standards except with our sample. We make the same standards in our sample.
Okay, so that's true. So let me back up to that. Why do you even want to do this? Why would one even propose doing a method of addition of a sample like a natural water sample?
You want to see if when you add the analyte without any potential matrix interfering, if it changes the response in a predictable way.
Right, so if we back up on the very first day of this class, we know that there is a relationship that we assume between the concentration of our analyte and the responsing instrument, right? And this linear relationship it manifests for most of us as a standard curve that you demonstrate that relationship is. This is fundamental to analytical science. And this relationship assumes that when we have a standard that's nice, 5% nitric acid and nothing else in there is really pretty looking, that this relationship in that nice pure standard is the exact same relationship it is in samples. But of course, that's often not the case, because in samples we have other things, most of the time, which we're totally unaware of, other components in that sample that may influence this relationship. Right? And so now we know in atomic absorption that our whole goal is to take sample analyte in this unknown sample and ultimately, through the analysis process, generate free atoms in the gaseous phase in the flame for us then to allow them to absorb photons. And there's a lot of things that can affect the extent to which those analyte atoms actually enter the free atom gaseous phase in our sample so they can then absorb photons. And the most important of those things are the other things that are in the samples. Because we have a fixed amount of thermal energy in that flame, or whatever the thermal source is. In this case, the flame. There's a fixed amount of thermal energy in that flame. And other constituents in there that are getting vaporized and volatilized are sucking up that thermal energy, right? And they're robbing our copper atoms, who need that to get volatilized, they're robbing the copper atoms of that thermal energy. And so if we have a lot of other constituents in the sample, like what's one of your unknown samples?
Seawater.
Seawater. What's the major constituent of seawater?
Chloride.
Okay, salt. And so you have sodium chloride in there, a lot of chloride. So you're doing the same thing and with concentrations of the sodium, the chloride, and the seawater that are hundreds or thousands of times higher than concentrations of copper. And so the matrix of seawater is, of course, primarily a salt, and that salt is actually robbing the thermal energy in that flame. It's one of those things. And it's such high concentration just by the law of mass action, we may get interactions between the counter-anion chloride and our cation, copper, right? And those interactions with copper, like copper chloride, could also be affecting the extent to which this occurs. And so our underlying assumption that we started in day one may not actually follow in a complex sample that we're doing atomic absorption with, because the composition of the sample is affecting the extent to which this process is occurring. And therefore, we need to have some other method in which we can say, do I get essentially the same answer for an unknown sample when I compare it to an external standard curve where I assume the relationship is the same, as when I perform a method of addition where I do what you guys just said, is I essentially take my standard curve and I make it up in the matrix of my sample, right? And so if I have my standard curve that looks like this, and then I take up my sample and I essentially generate a standard curve in that sample matrix. And so when I have a concentration of, in this case, copper added here, this is my standard curve with my 0 down here, right? When I make up my standard curve within my sample matrix, I am essentially just now changing the elevation of this line. And now, in this case, if I see a similar slope, what does that tell me? It seems a very similar response concentration relationship. Oftentimes, especially in biological samples, you do not see the same slope. You see some slope that looks like that, right? And that tells us that there is a different relationship, and that we cannot assume that this relationship, the equation of this line, is going to adequately capture that relationship and allow us to determine concentrations in a sample of a complex matrix. And so we undergo this process always in the beginning, when we start some new samples, because we can't assume that that's true. We have to prove it to ourselves as analysts that that's true. And if we are lucky and we get the same slope and we get the same answer when we do a method of addition versus using the external standard curve, then we feel good and we can proceed the easy way. And our workload is reduced by a factor of 3 or 4. If that's not the case, then we have to do it the harder way, and our workload is reduced by a factor of 3 or 4.
When you preparing the standard with for the sample, do you make it the same way that you would make a regular, like for your actual standard?
So there's several things that they should have talked to you about in class, and I'll come by today in lab, and I'll come by today and tomorrow to underscore that. One is that the standards that you use to make up your standard curve, you should use the same standard or the standard that begot these standards to make up your standard addition. Okay? You are generating a relationship here, and if you then make up a totally separate standard that you're going to use for a method of addition, and you make a mistake in making that standard, then you're going to get different numbers and reach a conclusion that the relationship is different between the response and concentration when it's not. Okay? So one example is you start from 1,000 ppm. I hate that term, you all know that. From that minute you make up a 100 ppm intermediate standard. And from that, many of you have been making up all your standards, right? 1, 5, 10, or whatever, right? And these are the ones you analyze and you plot, right? Now, the whole goal of doing a method of addition is that you want to essentially create a standard curve in your sample matrix without changing the sample matrix. If you take your sample, like seawater, and you dilute the hell out of it, and make a method of addition, then you can't even ask the question, is there a matrix problem? Because I've diluted the matrix out so much. So the optimal approach is to always have, a small amount of standard that you would add within a large volume of sample. So that the dilution of your sample matrix by adding your standard to do the method of addition doesn't significantly change that matrix. That makes sense? That's really important. Okay? So when you do this, then you would say, all right, I'm going to take, for a method of addition, we're actually out of time, but I'll go this in class, where I'm going to make up maybe 4 flasks that I'm going to analyze, and I'm going to add different volumes of the same standard in each of those flasks. So maybe I'll have a standard, that's let's say, a 0.5 micromolar, and here I'll add 0 microliters, here I'll add 100 microliters, here I'll add 200, and here I'll add 300. Okay? And then I'll add a certain amount of sample, let's say, and the amount of sample you add to all of them will be the same. That's going to be, 7 mils, same there, same there, same there. Right? So now I'm adding a small volume of standard, 300 microliters at most, to a large volume sample, so I'm not diluting my sample. And then I dilute the final thing to the same volume, which would be 10 mils in this example, right? This is one way to do it. There's several ways to do it. And the whole idea is that you're taking your sample, like I said, and generating a standard curve in that sample. That's the point.
Once you add the first two columns make sense, but do you have to dilute it to a different?
There's several criteria there's several factors that are important. One is the total final volume is exactly the same across all these additions, right? That's one. 2 is the volume of sample is exactly the same across all these additions. And 3 is the concentration of copper from your standard, at least doubles or triples across this. So you don't get a line that looks like that, but you get a line that looks like that. I'll come by lab, we'll go over this today to make sure everybody's really clear on this. If it's not, you come out of this, after doing this today and on Monday, if it is not perfectly clear, it's very important to talk about it. The assumption is that I get it. Ask you to talk about it in the lab.
You want us to make this for duplicate as well?
Yeah.